has all of the important equations for that chapter with a little bit of explanation. So a good way to study for the midterm exam is to look over the items in that page called the exam study guide. Review that page. Also, you're allowed to use an equation sheet during the exam. So you want to have a sheet of equations. A good way to get the correct equations written down is to copy the equations from the exam study guide. Put those on your equation sheet. Then you can refer to those when you're taking the exam. Now, of course, you have to understand the equations. Just having the equation written down isn't enough. You have to understand what it means. That's why you should review each item in the study guide. Make sure you understand the meanings of the equations. So for example, here's chapter 25. Here are the equations that you would find in the exam study guide for chapter 25. What is it? 10 equations. And these are the familiar equations. I is dq over dt, that's the current. J is I divided by A. J is the current density. I is the current. A is the area of the wire. There's an interesting formula from that chapter that relates macroscopic current to microscopic parameters of the material. If this is a current in a metal, then the current density is negative E times the density of electrons times the mean velocity of the electrons, or sometimes called the drift velocity, V sub D. We're also considering resistance. So the resistivity is defined as the electric field divided by the current. That's a property of the metal. So each metal has a different value for resistivity. Or we also define conductivity. 1 over the conductivity is equal to resistivity. And in particular, the resistance of a wire is the resistivity rho times L over A, where L is the length of the wire and A is the cross-sectional area of the wire. So a longer wire has a larger resistance, and a skinnier wire has a larger resistance. There's an equation relating resistance to temperature. This is Ohm's law. Relates the current in the wire to the potential difference along the length of the wire. These are the equations that show how to combine resistors in series and resistors in parallel. And finally, the power. The power, for example, the power dissipated as heat in a resistor is I squared R. So, if you had these equations, you'd probably have all the equations that you would need for problems in chapter 25. But of course, you have to know what they mean. So that's why you have to kind of review what it says. So I would say that's a good way to prepare yourself for the exam, is making up that sheet of equations. And you can find a study guide at the end of each chapter. Now, the main thing I want to do in tonight's Zoom meeting is to go over some hints for some of the Lon Kappa problems. So here's one of the Lon Kappa problems from homework assignment number 4. This is the problem. You have a wire, and half of it is made of a metal with conductivity sigma 1. The other half of it is made of a wire with conductivity sigma 2. There's this junction where the two parts are soldered together. Current comes in one end, goes out the other end, an equal amount of current. Sort of a 1 amp comes in one end, then 1 amp must go out the other end. And there will be a net charge at the junction. And that's the problem, is to calculate the net charge at the junction. This is actually a problem from the textbook, and it's also assigned in Lon Kappa, but it's a problem from chapter 25 in the textbook. There are some hints already given with the problem. The hints tell you that you're going to use the current density, so that's J, and the conductivity is given, so you're going to use the equation for conductivity. Well, current is current density times area, so that's J, and J is sigma E, that's Ohm's law, where sigma is the conductivity. That's one way of writing down Ohm's law. So let's see how we would calculate the charge at the junction. You know, suppose this gray metal has a very large conductivity and the orange metal has a lower conductivity. Then, as you might expect, there'll be some charge accumulating on the junction because it's coming across this wire with a larger current than it is going out this side. Well, no, the same amount of current comes in and goes out, but in equilibrium, there will have developed a kind of a net charge at the junction. So it already says use these two equations. And these are the two equations that you would have on your equation sheet for the exam. I is J times A, and J is sigma times E. All right, so that's kind of given in the hint. Now what we're trying to calculate is Q. So where does Q come into it? Well, there's the famous equation called Gauss's law. Gauss's law relates the flux of the electric field to the charge. It says the flux out of a surface S. So if you have some surface S, closed surface S here, and you calculate the flux of the electric field coming out of that surface. So let's say going out on this side, maybe going this way on this side. Well, might as well assume that it's going in on this side. The electric field, the current's going in this way, so the electric field should be pointing in this way. And the net flux is the charge enclosed. Well, the charge enclosed is exactly what we're trying to calculate. We're trying to calculate what's the charge at that junction. So we put up a little Gaussian surface here, a little cylindrically shaped surface here, where the junction occurs. Now I can solve this for the charge enclosed, multiplied by epsilon 0. The flux of E, well, this is metal number 2. Over here is metal number 1. So the flux coming out of metal number 2 is E2 times area. Flux is field times area. And it's the outward flux. So it's the flux to the right. Now, as for the other side, the flux will be minus E1 times A. It's again the electric field, which on this side is E1, times the area. But in this case, it's negative because the electric field will be pointing into the surface. And we're calculating the flux out of the surface. So that'll be negative E1A. And here's the equation for Q. So that's the solution to the problem. Of course, you have to put the solution in the form of the quantities that are given. And in particular, in terms of the conductivities. So for E2, I would have J divided by sigma 2. And what's J? J is I divided by A. So E2 would be I divided by A divided by sigma 2. And then minus E1 will be I divided by A divided by sigma 1. And you see, interestingly enough, the area cancels out as long as the area all along the wire is constant. The areas will cancel. And so we just have epsilon 0, that universal constant, times I, times 1 over sigma 2 minus 1 over sigma 1. If there were no junction here, then sigma 1 and sigma 2 would be equal. And then there would be no charge accumulated at the junction. But if sigma 2 is larger than sigma 1, then there'll be a negative charge accumulated at the junction. All right, so that's an example of a problem where you have to put together a number of different equations. And in particular, you have to use Gauss's law, which gives you the relation to the charge. So that's the kind of problem that on the exam you would want to have those equations handy on your equation sheet. So let's go on to another of the line capital problems from homework assignment number 4. What's the drift velocity of a conduction electron in gold? So you have a gold wire with a length L and a cross-sectional area A, and a current I equals 1 amp. So you have this wire. And the cross-sectional area here is A. And the length, I guess it'd be this distance, is L. And the goal is to calculate the drift velocity. Well, again, there's only one equation that mentions the drift velocity. So obviously you're going to need the equation from the equation sheet. Current density is E times N sub E times V sub D. V sub D is the drift velocity. That's what we're trying to calculate. E is just the charge of an electron. We put in here minus sign because the electron is negatively charged, so the direction of the velocity is opposite to the direction of the current. But we're just calculating the magnitude anyway, so we don't have to worry about the sign so much. Now, what we're given here is the current I. So we have to substitute for J, I over A. We're not given J, we're given I. And the cross-sectional area A. So if you put all this together, the drift velocity will be I divided by A, that's J, divided by E, divided by the density of electrons. It's not the density of all the electrons, it's the density of the conduction electrons. Now, to get any further, you have to know this electron density, because the other quantities are given. So what's the density of conduction electrons? Well, for most metals and for gold, there's one conduction electron for each atom. So the density of electrons is the same as the density of atoms. And you can figure out the density of atoms from the mass density. It's the mass density, the number of kilograms per unit volume, divided by the mass of a single atom. So this will be kilograms per cubic meter divided by kilograms. So this will be the number per cubic meter. And we're actually calculating the density of atoms. What we need is the density of electrons, conduction electrons, but they're equal. Now you have to look up and maybe you have to do a Google search or something like that to find out what's the density of gold. If you look, if you do a Google search for density of gold, you'll find 19.32 grams per cubic centimeter, or times 1,000 kilograms per cubic meter. So that's the density of gold. Gold has a rather high density. The density of water is 1,000 kilograms per cubic meter. Density of gold is 19.5 times larger. You have to know the mass of a single gold atom. And again, you would look it up on some table of atomic masses, or maybe look it up on a Google search. It's 197 atomic mass units. The official name of the atomic mass unit is the Dalton. 1 Dalton is 1.66 times 10 to the minus 27 kilograms. You have to make sure you have consistent set of units. So just use the standard units, kilograms and meters. Well, then you have to convert the mass here into 197 times 1.661 times 10 to the minus 27 kilograms. So now this determines N sub E. A is given in the problem, I is given in the problem, E is just a charge on an electron, so that's a universal constant. And the rest is just use your calculator. But before you use your calculator, you really ought to derive the equation. That's the easy way to do it. The easy way to do these physics problems is don't start putting in the numbers until you've actually analyzed the equations. So start by using algebra to get the equations. And then once you've got the equations, then you can just substitute in the numbers. That's a lot easier than substituting in the numbers from the beginning. So let's see what we get. Well, let's just make a rough estimate. I won't calculate it exactly for gold, but I'll just make kind of a rough estimate. The density of electrons is we call this 2 times 10 to the 4th, 20 times 10 cubed, 2 times 10 to the 4th. That's mu, divide by M. M is 197, well, I'll call it 200 Daltons. A Dalton is 1.66 times 10 to the minus 27 kilograms. So now this will be the density of electrons. And as you can see, it's something like 10 to the 4th divided by 10 to the minus 25. So it'll be something like 10 to the 29th. It's roughly 0.5 times 10 to the 29. But here's where you would use your calculator to get the exact number here. And then as for the drift velocity, you have the current, 1 amp is 1 coulomb per second, divided by the area. Not sure what value of area is given. Divided by the charge of the electron, 1.6 times 10 to the minus 19 coulombs, divided by this density of electrons, 0.5 times 10 to the 29, rough estimate. And you see, if you just look at the powers of 10, it's something like 10 to the 29 minus 19. So something like 10 to the, no, it's 1 over that. 1 over 10 to the minus 19 times 10 to the 29. So it'll be of the order of 10 to the minus 10. Calculated accurately with a calculator. It'll depend on the area. I haven't put in the area. The area was some number of meters squared. So the answer will come out in meters per second. See, the units worked out correctly. Meters cubed divided by area is meters, divided by seconds gives me meters per second of velocity. And you can see it's very slow because it's got this power of 10 to the minus 10. So electrons that carry the current in a metal wire move on the average very slowly. Only 10 to the minus 10 meters per second. Part B of the problem is to calculate how long would it take, how many hours would it take for a conduction electron to drift from one end of the wire to the other. But once you know the velocity, it's very easy. The time will be the distance over the velocity. And I don't know, the distance is given in the problem. This will turn out to be some number of hours. So currents, the electrons in currents travel very slowly. Of course, that raises the question, why is it when you turn the switch on for a light bulb, the light bulb lights up instantly? You don't have to wait for some period of time for the electrons to get to the filament. That's because the electrons start moving in the filament as soon as there's an electric field. Now, the electron travels slowly, but the electric field travels at the speed of light. So the electric field will, appear in the filament more or less the instant that you flip the switch. And as soon as there's an electric field, there'll be a current, because J is sigma E. So although individual electrons are moving slowly on the average, the electrons will appear in the current almost instantly. All right, so that was another problem from homework assignment 4. Here's another problem from homework assignment 4. This is another problem from the textbook, because I don't have it written down here, but this is one of the problems at the end of the chapter, in chapter 25. You have a current which is coming in at some point A and going out at some different point B. So you have a wire here. You have a wire connecting A and B and connected to a battery. So you have a wire like this. I guess if the current is going to go this way, this has to be the positive terminal of the battery. This is the negative terminal of the battery. And so it drives a current into point A and then out of point B back to the battery. What's the resistance? Now, of course, you know the relation between resistance and voltage is Ohm's law. So the voltage, well, I guess the voltage divided by the resistance will be the current. But what's the resistance? This is an example of two resistors in parallel. This region of the circle, this quarter circle, is one resistance. And this region of the circle is another resistance. This resistance is 1/4. No, this resistance is 3 times larger than this resistance because the length is 3 times larger. Remember, resistance is resistivity times length over area. The area is constant around the cross-sectional area is constant around all around the wire. So you have a small resistance here, a larger resistance here by a factor of 3, and you want the total resistance. So this is a problem where you have two resistors in parallel. So again, you should have memorized, or at least written on your equation sheet, the way to combine resistors in parallel. The resistance is R1, R2 over R1 plus R2. Now R1 and R2, again, you'll need the equation from your equation sheet. Resistance of a wire is rho L over A, where rho is the resistivity. If we say this is a copper, a circle made out of, a ring made out of copper wire, you need to know the resistivity of copper. I think in the textbook there's a table of resistivity, so you can look up the value of rho. Or you could do a Google search. You just search for resistivity of copper.
Would it give it to us on the exam?
What's that again?
Would it give it to us on the exam? Like, so we don't have to look
Yeah,
it
yeah,
up?
you wouldn't have to look this up on the exam.
Okay.
Now the length, well, it's 1/3 of it's 1/4 of the circumference here, and it's 3/4 of the circumference here. So we have a common factor rho over A, and then we have the arc lengths, 1/4 of the circumference and 3/4 of the circumference. So we have common factor rho divided by A, L1, L2 over L1, L plus L2. L1 is 1/4, L2 is 3/4. So it'll be 3/16 times rho times the circumference of the circle divided by the cross-sectional area of the wire. So again, this is the kind of problem where you need to know several equations and how to put together, and then you have to put them together. Now that's not all of the ln kappa problems. That's not even all of the topics in the ln kappa assignment. There are also some problems in that homework assignment number 4 about circuits, DC circuits. Circuits with a battery and maybe a resistor and maybe a capacitor. But since there's just a battery to drive the current, that's a direct current circuit. Any point in the circuit, the current will be in the same direction. Current won't be oscillating back and forth between two different directions as it would in an alternating current circuit. So I didn't prepare any examples, but for example, there's one problem on RC circuit where you have a circuit with a battery and a resistance and a capacitance, and you're charging the capacitor. That problem is solved in section 26.5. That's in chapter 26. So make sure you get the equations from the solution of that problem in section 5. Then the problem goes a little bit beyond that. The problem asks about energies. So you also have to remember some equations involving energy. So for example, the energy of a capacitor is Q squared over 2C. So from the solution of the RC circuit problem in section 5, you'll know how Q depends on time. This gives you the field energy, the electric field energy inside the capacitor. I think it probably also asks about the power dissipated in the resistor. So again, you have to know the power dissipated in a resistor is I squared R. And again, if you read section 5, you'll find the equations for Q, which depends on time as the capacitor charges, and I, the rate at which charging occurs, is the current. There's another problem here, which is probably the most difficult of the problems. It's a two-loop circuit. So I don't have it drawn here, but you have, it seems to me you have a battery, and then you have one loop, and then you have another loop. And I think there's a resistance here, and there might be a capacitor someplace. Maybe there's a capacitor here, not quite sure, resistance here. Anyway, the point is there are two circuits here, the two loops. And really the only way to do this problem is to use Kirchhoff's laws. So you need to study sections 1 and 3 in chapters 26, which explains Kirchhoff's laws. Kirchhoff's laws, there's one equation for each loop. So you're gonna have two loops, you'll have two equations. So you sort of have Kirchhoff. So you sort of have two equations with two unknowns. We'll solve that by, it's actually differential equations because you're charging a capacitor. So the current, this current, there are actually two currents. There's a current that comes down to the capacitor. There's also the current that goes through this resistor. But this current is equal to the derivative of Q, where Q is the charge on the capacitor. Because, let's see. So you're going to have you're going to have several equations, and you'll have to solve a differential equation. It's a lot like the one loop problem. It'll have an exponential solution, but this will be a little more challenging than the other problems, I think. So that's all I really had prepared for tonight. Let's see if there are any questions in the chat. Well, this is the answer to a question. Is this being recorded? Yes, I think I've got this recorded, and I'll put the recording on the YouTube channel. It's the same YouTube channel where there are some short screencasts, some video screencasts about the material for each week. Could you go back up to that after this problem? Up to what?
Oh, I was talking about the resistance problem of the semicircle.
Yeah, the resistance of the ring. Yeah. What was the question?
I just wanted to see the last part. I was trying to write that part down.
Oh, okay. Well, all it really is this and this. So those are equations you would have on your equation sheet from preparing an equation sheet for each chapter. The rest of it's just algebra.
All right, thank you.
Can you send the link of the YouTube channel? Let's see. The link of the YouTube channel. You go to YouTube and then you search for PHY 234. So in YouTube, do a search on PHY 234. I think that's enough to get you. There'll be a channel with my name on it, Professor Stump, and you click on that channel, click on the playlists. There'll be one playlist which consists of some short lectures, sort of screencast type lectures. And then there'll be another playlist, which is the recording of the Zoom meetings.
I found it, thanks.
Yeah. All right, so this has been a rather short Zoom meeting, but should be prepared to now finish homework assignment number 4 and then start studying for the exam. And like I said at the beginning of the Zoomcast, a good way to study for the exam, of course, the best way to study for the exam is to do the practice exam. So that's the best thing you can do to study for the exam. Of course, the best way to do the exam is to do all the homework problems. But assuming that you've done all the homework problems and you've done the practice exam, but you just want something to carry into the time of the exam, make an equation sheet, and a good source for that is the exam study guides at the end of each chapter. So any last questions?
I think this was already asked and answered. So for the resistivity of copper, is that something that we're going to have on our exam sheet, or would that be given with the problem?
That would be given with the problem. Otherwise, you would have to use Google or something like that to look it up. But no, that would be given with the problem.
All right, thank you.
All right, so I'm ending the meeting. Let's see, how do I do this? Oh, first of all, I've got to